Hey guys, in this video we're going to be talking about identifying quadratics and their key features. We're also going to talk a little bit about how to determine whether a table, graph, and equation is linear or quadratic. So in order to do that, the first thing we're going to do is review what a linear function looks like in each of those formats. So when it comes to a graph, so linear graphs can take a few forms. First of all, they are all straight lines. No matter which direction they go, all linear graphs are straight lines. So you have positive linear graphs that go like this. You can have a negative linear graph that goes the opposite direction. You can have a vertical line, that's the x equals graph. You can also have a horizontal line, which is the y equals graph, okay? Now, when it comes to linear tables, the key here is that there is a constant rate of change in what is called the first difference. So constant change in the first difference. Now, that first difference, those two words together, might be new for you. We know that, or we've always talked about, how a linear table has a constant rate of change. But when we start talking about quadratics, it's important to understand that the constant change occurs in the first difference. Because when you get to a quadratic table, it still occurs, but it happens in the second difference. So let me make up a table here. Let's say that my y-intercept is at 5 and my constant difference is 2. So that means it would go 7, 9, and in the reverse order would be 3, 1. So in the first difference, we see here that the y value is increasing by 2 for every 1 increase in the x value. So this is the first difference when it occurs right away, okay? And we'll see more of that here when we talk about quadratics. Now, finally, when you talk about linear equations, it's important to note that the x term is not any higher than the first power, okay? So it has a degree of 1 for most of the cases. So degree of 1 means the biggest exponent is 1. So the most common that we see is slope-intercept form, like y equals negative 4x minus 2. That's an example. That's x to the first power. We've also seen them in standard form, so that would be like 2x minus 3y equals, 9. Again, x to the first power here. We could change this to look like slope-intercept form. We've also seen it in point-slope form, where you have something like y plus 5 is 1/2 times x plus 1. Once again, still just x to the first, can be written into slope-intercept form. We've had the vertical line, so that's x equals 4. Now the only one, again, x to the first, the only one that's a little bit tricky is when you get to the horizontal line. Because you have y equals, we're going to make up a number here, 3. Technically, this is x to the 0 power, but it's still not bigger than a degree of 1. So it is still a linear equation. All right, so all of that is important to know because we're going to be comparing linear equations to quadratic graphs, tables, and equations. So that's where things differ. So let's talk about their graphs first. So quadratic graphs, or quad graphs for short, are what is called a parabola. So it opens, it's a U shape, first of all, that's what a parabola is. It can open up or it can open down. It cannot open to the side because then it would no longer be a function. We don't talk about that here in Algebra 1. Okay, so that's what the graphs look like. Quadratic tables are different in that the constant change does not occur in the first difference, it occurs in the second difference. Okay, so let's see if I can make up a table here without messing it up. So if we have x and y, I'll still use -2, -1, 0, 1, and 2. Let's do, we'll start at 0, 0. We'll make it easy. So then 1, 4, 1, 4. Okay, so to go from 4 to 1, I know I have to subtract 3. To go to from 1 to 0, though, I don't subtract 3, I subtract 1. So I already know this is not linear because it's not a constant rate of change in the first difference. From 0 to 1 is adding 1, and from 1 to 4 is adding 3. Now what makes it a quadratic here is what is occurring in the second difference. So let's take a look at that. To go from -3 to +1, I need to add 2. To go from -1 to +1, I also need to add 2. And to go from 1 to 3, I also need to add 2. So here is where the second difference occurs. This is the first difference. This is the second difference. So that means that this table represents a function that is quadratic. Now finally, equations. The degree is always 2. That's what makes it a quadratic. There are 3 forms of quadratic equations. The most common is in standard form. So it would be something like y equals x squared minus 2x plus 6. And that's just one example. There's also something called factored form. So that would be like x minus 5 in parentheses times x plus 3. And the final form that we don't talk about too much is called vertex form. So that's where you would have something like x plus 2 squared minus 7. That is vertex form. All 3 of these are examples of quadratic equations. So let's practice. First, we want to identify whether each of these graphs is linear or quadratic. So basically, you just need to understand the shapes of the 2 types of functions. Remember that linear creates a straight line. Quadratic is a parabola or a U shape. So that means anything that's a straight line is linear. So number 1 is linear. Number 2 is not. That's a parabola. That's going to be quadratic. Same thing with 3. 4 is a straight line, so this is linear. 5 is a straight line, so that one's linear. And 6 is also a straight line, so that one is linear. So those 4 are linear. Numbers 2 and 3 are quadratic. The graphs are usually pretty easy to tell. It doesn't require too much work. All right, let's take a look at some tables, or sorry, some equations. So again, we're focusing on the x and what kind of exponent it has. If it's a 2, it's going to be a quadratic. If it's 1 or smaller, it's going to be linear. Okay, so again, this is x to the first, making this one linear. This one is x to the second, so this one is quadratic. This is y equals 6, so that's a horizontal line. That one is linear. This one is also to the second power, making this one quadratic. And this final one here is the trickiest one. You have to be careful. If you have 2 sets of parentheses together like this, you have to remember that this means multiplication. So that brings us back to our box method. And you don't have to do this every time. As long as you eventually recognize that 2 factors next to each other like that is going to give you a quadratic, you'll be in good shape. But since it's our first time talking about it, let's go ahead and see what happens when I multiply these 2 together. So I'm going to have x and -2 and x and +3. X times x is x squared. X times -2 is -2x. 3 times x is 3x. And 3 times -2 is -6. I'm going to combine my like terms here. So I'm going to have x squared plus x minus 6. There's that squared right there, making this one a quadratic. So anytime you have two sets of parentheses next to each other like that and there's an x in both of them, it's going to be quadratic because you're going to end up multiplying those x's together. All right, now let's take a look at some tables. So again, the key factor here is understanding that linear tables have the same difference, or a constant change in the first difference, and quadratics are in the second difference. So let's take a look at that here. So this one, to go from 14 to 10, I would subtract 4. From 10 to 6, I also subtract 4. So it's looking linear so far. Minus 4, minus 4, minus 4, minus 4. This one is linear. It's also important to note the x's are all increasing by 1. So that's why I don't have to worry about those too much. If they were increasing by different amounts, I would need to see if there is a constant slope throughout, but we don't need to worry about that today. All right, number 2, to go from 30 to 20, I subtract 10. To go from 20 to 12, I subtract 8. So I already know this is not linear. To go from 12 to 6, I subtract 6. 6 to 2 is minus 4. 2 to 0 is minus 2. And 0 to 0 is plus nothing, or plus 0. So let's check the second difference. 10 to negative 8 is plus 2. Negative 8 to negative 6 is plus 2. Negative 6 to negative 4 is plus 2. Negative 4 to negative 2 is plus 2, and negative 2 to 0 is plus 2. That's a constant change in the second difference, so this one is quadratic. All right, let's check the last one. 0 to 5 is plus 5. 5 to 8 is plus 3, so this one's not linear. 8 to 9 is plus 1, and then 9 to 8 is minus 1. 8 to 5 is minus 3. And 5 to 0 is minus 5. Let's check the second difference. Here I would subtract 2, subtract 2, subtract 2, subtract 2, and subtract 2. So once again, this one is quadratic because there's a constant rate of change in the second difference here. All right, moving on, let's talk about key features of a quadratic. So anytime you're given a graph, there are several things that you should be able to pick up on just by observing the graph. So the first of which is something called a vertex. Your vertex is either the minimum or the maximum point of your quadratic. This one's a minimum. It's right here where the curve happens. That is always an ordered pair, and in this case it is 2, negative 4. So my vertex is 2, negative 4. The equation of the axis of symmetry. That is the invisible line that runs through the vertex. It is a vertical line. What the axis of symmetry does is reflects one side of the graph to the other. So here's what I mean by that. If I drew my invisible vertical line through the vertex like that, I could literally take this part of the graph, fold it over that line, and it would match up perfectly with this part of the graph. That's why it's called an axis, or a line, of symmetry. It's matching on both sides. Now it's important to note that this is an equation. Since it's a vertical line, it is x equals, and it's always whatever the x value of your vertex is, which in this case is 2. All right, solutions, zeros, roots, x-intercepts, those are a bunch of words that all mean the same thing. They are where the graph touches the x-axis. Most of the time there are 2 solutions when it comes to a quadratic, but it is possible to have only one, and it is possible to have none. The none occurs when it does not touch the x-axis at all, and one occurs when the vertex is on the x-axis. In this case, we have 2 solutions at 0 and 4. So for the solutions line, I'm going to say 0 and 4. Do not use a comma here because then it looks like an ordered pair. And while you can write them as ordered pairs, neither one of these points is 0, 4. This one is 0, 0, and this one is 4, 0. So it's up to you how you want to write it. All right, the y-intercept is exactly as it sounds. It's the place where the graph touches the y-axis, which happens to be one of our solutions here. So the y-intercept is at 0, 0. In this case. All right, domain and range is something we haven't talked about in a while. So remember, domain are all the x values that are used in the function. Now, a lot of times we're going to talk about this in terms of context. But so far today, we're not dealing with that. We are just introducing the parts of a quadratic. It's also important to note that this quadratic is supposed to have arrows at the top here. The graph, the software that I use just doesn't put them. So you have to understand that those are there. So when it comes to domain, remember you're trying to find the farthest left the graph goes to the farthest right. Now the farthest left I see is an arrow, so that means it goes to negative infinity forever. And the farthest right the graph goes is also an arrow, so that's infinity. So I'm going to write negative infinity to infinity. All right, now the range on the other hand is bottom to top. So the bottom of the graph occurs in this case where the vertex is. It's right here at -4, and that's inclusive here, so I'm gonna put a bracket instead of parentheses. But up at the top, I have arrows. That means they go up forever. So that means my range also goes up forever. So it's from -4 to infinity. And that's it for this one. Let's try another. All right, so this graph, the main difference between this graph and the last one is that this one opens down. And we will investigate what makes that happen at a later date. All right, so let's start with the vertex. This time it's a maximum. It's right here. That's -2, 1. The equation of the axis of symmetry runs through that point as a vertical line. So it's x equals -2. This one still has two solutions. One of them is at -3. One of them is at -1. So I'm going to say -3 and -1. All right, so let's talk about the y-intercept. This time it is not one of the solutions. It's right here at 0, -3. And then when we talk about our domain, once again, arrows on the left and the right. So it's negative infinity to infinity. The range, however, is not the same. So this time the arrows go down forever. So it's going negative infinity forever. And its maximum point is at our vertex, which is a y value of 1. So that would be the range. I think we have one more in this packet. No, we're going to talk about some real world scenarios. So same idea, but now we're going to have some context with it. Okay, so this problem says a baseball batter pops a ball straight up. The height of the ball is shown as a function of time in the graph. What types of information can be learned about the height of the ball? So basically, we're going to answer the same questions. Okay, so let's start with the vertex. So the vertex here is right about there, and we're going to have to estimate a little bit because it's not quite 70. It is at 2 seconds though, so it's 2 and about 68 or so. So we're going to call this, so for the vertex, I'll write it down here, is at about 268. Now the axis of symmetry, the equation of that, runs straight through that vertex. So the axis of symmetry, or AOS, is x equals 2. Okay. Then we have the solutions. So this one also has 2. It appears like it's going to hit back here somewhere and also right here. Now for this one, it's important to note that this is a real world scenario. If I have an answer that is in the negative region, can I have a negative amount of time? Short answer is no. So we do not pay attention to that negative solution. If this did not have context, we would write it down as a solution. But for this one, it doesn't make sense in context, so we throw it out. The only solution is right here, which is about 4.1. Okay, so our solution is 4.1. All right, then we have the y-intercept. We can't quite there it is, right about there. Once again, we are estimating, which is okay for this context here. This one, the y-intercept is about 8, so we'll say 0, 8. And then we have the domain and the range. So domain, again, even though this graph is going to continue this way and hit the negatives, it doesn't make sense for our domain here. So time starts at 0 and stops at our solution, which in this case is about 4.1. So my domain this time is going to have brackets on both sides because it's inclusive. And then the range is something similar here. So the bottom is going to be here at a height of 0, and it goes all the way up to our vertex, which we said was 68. So the range is from 0 to 68. All right, now the last thing that we didn't talk about in the other ones because it had no context was this question right here. What do each of these mean in the context of the problem? So let's talk about that real quick. So the vertex here, 268. What that means is at 2 seconds, the ball reaches a maximum height or a max height of 68 feet. So your vertex here, remember, is always a maximum or minimum. Okay, so in this case, it's a max. So it's a maximum height because that's what the y value is talking about. The axis of symmetry we don't talk about too much as in the context of the problem, so we'll skip over that one. The solution, 4.1, means that the ball hits the ground at 4.1 seconds. So the batter hits the ball, it goes up, up, up. At some point it reaches its max height and then starts falling back to the earth and hits the ground at 4.1 seconds. All right, the y-intercept, 0.8. That tells you the starting height, in this case, of the ball. So the starting height of the ball was 8 feet. Okay. All right, so let's talk about the domain and the range. So the domain goes from 0 to 4.1. So what that means is the ball was hit at time 0, and it increased and decreased and then fell back to the earth at 4.1. So ball was hit at time 0 and was in the air for 4.1 seconds. All right. Now the range is similar, except it's not talking about time, it's talking about height. Okay. So the ball reaches a maximum height of 68 feet and a minimum height of 0 feet. So the ball had a min height or minimum height of 0 feet and a max height of 68 feet. And that's it for that one. I believe we have one more, two more, one more. Two more. All right, here we go. The graph to the right represents the height of a skier after she has jumped off a ramp. Use the graph to find the key parts of the graph. Okay, let's start with the vertex, and then we'll also talk about what each part means. Okay, so the vertex, again, is right here. That's at 216. So 216. So what that means is, in 2 seconds, the skier reaches a maximum height of 16 feet. All right, the equation of the axis of symmetry is also right through that point at x equals 2. All right, our solutions, zeros, roots, x-intercepts, etc., are at -2 and 6. And again, we're talking about, I assume, time here. It didn't necessarily tell us, but it's usually time versus height. So it makes no sense for us to have this negative solution. So we're going to throw it out. So that means our solution is 6, which means after 6 seconds, the skier reaches the ground again, or the snow again. She's no longer in the air. All right, so let's talk about the y-intercept, which is right here at 12, or 0, 12. What that means is when the skier hit the ramp, she was 12 feet in the air, or when she left the ramp. So that's pretty high up in my opinion. All right, domain. So once again, we see that the x values continue this way and this way. There are actually arrows down here in the photo, but it is a real world scenario. So once again, if x is time, it starts at time 0 and stops at our solution, which is 6. So it's from 0 to 6, which means that the skier jumped off the ramp at time 0 and was in the air for 6 seconds. The range starts at the bottom. It's from 0 and stops at the highest point, which is 16. So 0 to 16, meaning that the skier had a minimum height of 0 feet. That's when she lands back on the ground, and a maximum height of 16 feet. Okay, let's try one more. The graph to the right shows Tarzan's height over time as he swings through the trees. Use the graph to the right to find the key parts of the quadratic, and once again, we're going to talk about what each of these mean. All right, so the vertex this time is a minimum. It's at 3, 1. And what that means is in 3 seconds, in this case, it's not a maximum height, it's a minimum height. So in 3 seconds, Tarzan reaches his minimum height of 1 foot. Okay, 1 foot off the ground. The equation of the axis of symmetry runs through that point. So that's x equals 3. Now, if you notice, the graph never touches the x-axis. So what that means in the context here is that Tarzan never touches the ground. So there are no solutions, or none. You can say the word none. And again, in the context, that means that he never touches the ground. The y-intercept is right here at 0, 7, which means that when he first started swinging in this particular swing, he was 7 feet off the ground. Okay? All right, we don't talk about the domain and range for this one, but I could go over it quickly here. So for this particular swing, he starts at time 0 and then he just keeps going forever. So it would be 0 to infinity because he's just continually swinging through the trees. The range starts at 1, so it's from 1 to infinity because he could, well, it's probably not infinity. It would be whatever the top of the tree is, which we don't know. So this would be one of those cases where we would say it's 0 to the top of his swing in this case. All right, but that's it. That's how you determine whether something is linear or quadratic in different forms, and how to find the key parts of a quadratic.